All right, so again, I'm Alfredo. Since it's too long, you can just call me Alf, it's fine. Also, feel free to follow me on Twitter and post, picture from the talk, or if you found something that is useful for you, share your opinion. It means something to me. All right, so today we are going to be talking about convolutional neural networks. Ooh, right? All right. So basically, we are going to be exploiting the stationarity, locality, and compositionality of the input data, which is basically most of the time natural data. So it's data that is captured with some sensors from reality. And therefore, given that these are basically the transduction on some natural signal, they will have some properties, which are namely these three guys here, which can be exploited in order to improve the performance of our model. Okay. All right. So again, as last time, I just made these slides a few hours ago. So there are going to be some mistakes. If you don't understand what's going on, there are going to be errors, perhaps. So just stop me, ask me anything. Don't let me go, because again, if I lose you, it's very hard for me to get you back on. Okay. Deal? Thank you. All right, so let's get started. Nice picture of a cat. All right, so signals can be represented as vectors. For example, if we deal with one-dimensional tensor, like we have seen last time, which means it's a vector, we can, for example, represent a waveform wherever every sample, the height of the sample, maybe represent the air displacement measured by a microphone. So in this case, xt is a waveform height. Those numbers here. So there is a t here because I usually have vectors as column vectors in my mind. So although I wrote them as a row, they are vectorial. I mean, these are column vectors. On the other case here, we have a cute cat. And we can also think about that as one-dimensional tensor, so it's a vector, whereas in every element here, I have all the pixels. So for example, here I have the first row, then I have the second row, and so on. So I can think this kitten here as one point in a, I don't know, let's say it has 10 pixels times 10 pixels, white and black, so grayscale. So I can think about this cat as one point in 100-dimensional space, okay? So all the cute kittens can be, move up the thing, all right. Okay, sweet, thank you. So we can also think about this kitten here, if it's like a 10 pixel times 10 pixels grayscale, is one point in 100-dimensional space, okay? Another point maybe is another kitten, and so on. And in this case here, my x, I, j are pixel values. Most of the time, perhaps we are representing this guy here with a better representation, which would be a two-dimensional tensor or a matrix, wherever we have like in the y-axis, like so over the rows, we have the pixels that are vertically distributed here, and across the row we have these pixels over here. Maybe that's a better representation than just having everything in just one long vector. Why do I represent this guy as a one long vector? Because yesterday we have seen that for playing with basic neural networks, I just have vectors and matrices, and then I have this kind of a fine transformation of vectors. So we are going to be seeing later on the notebook, we are going to be playing just with this kind of vectors and matrices in order to move kittens around. Finally, we can also represent John picked up the apple sentence as a sequence of words. And in here, every xt are perhaps one hot vectors, which are basically representing which word out of a dictionary is being used in that specific position. So x1 may correspond to John, x2 may correspond to picked, and for example, John may be the, I don't know, whatever word in the dictionary. Like you open your dictionary, you look for the word John, you count what is the position from the beginning, and that's going to be corresponding to the position of that one in your vector that is long as many, so it has the size of as many words in your dictionary. Okay, does it make sense? It's the one hot encoding from yesterday. Yeah?
Is that how a lot of natural language processing works? There's just having the same long vector with just all the different words?
Yeah.
Cool.
Yes, yeah. So you start with that one, and then you may collapse into some more condensed version, which is basically a embedding representation on that kind of one hot. But again, you start with the one hot at the beginning. All right, so these are different kind of signals we can represent, like audio, we can represent images and text. Everything can be represented in a vectorial format. In this case, just one-dimensional tensor, right? So it's a vector. All right, so what are the particular properties of using natural data? Because again, this is an audio signal, this is an image, and this is also a natural language. So all of these signals have some specific characteristic. They are natural, they look natural to us. What does it mean? So let's see something better here. So let's pay attention to the first audio signal. We are gonna be seeing that here, for example, in the left-hand side, we have this kind of sinusoidal kind of waveform. But again, later on, also we have the exact same sinusoid happening in two different locations, right? So the same kind of small representation, like small detail, may happen in two different parts of the signal, right? Now we can just have a look, we can look at a larger part, and we can think, for example, that this peak here, it's happening again here, and maybe that same waveform is also there, and we don't really care where it is. So, I mean, we observe the same kind of pattern in multiple locations across the, for example, temporal domain, the temporal axis in this chart. So we have to pay attention to this part. Natural signals show some kind of repetition on the same kind of patterns over their dimensionality. All right, so let's go back to our kitten here. So let's focus on a particular detail, right? Like before we observed the sinusoidal part, when we zoom in the waveform, we can just focus here on the nose. So let me zoom up a little bit, so okay. It's like a monster. All right. So what we can notice here, this kind of particular shape in this circle here, it may be very similar to whatever happens here. So it's like a darker region surrounded by lighter pixels. So similar things, again, are recurrent. No? They appear again in different regions of our signal. In this case, we move spatially, so this space in this two dimension before we had time across the x direction. Also, we can notice what is the likelihood, what is the probability that those two pixels here, this one and the other one, are of the same color. Question to you. It's very high, right? So pixels that are close together may have the same color. What about this one? Not that high, right? Because you go further away from that neighborhood. So things may change, right? If you start looking around with more distance. What about now? They are completely different, right? We get a black pixel at the beginning, and now we see a white pixel, basically, almost. And of course, the further you go away, and the less related pixels are. So in here, we also capture, we can think about two different characteristics. First one is that we have specific features co-happening, like happening at the same time in different locations. And then we have that things that are close together are fairly similar, that as long as you go away, they look not that similar. So basically, here we can think about this one, this stuff as stationarity of the signal. So the signal presents the same kind of patterns over and over again. So stationarity is the first word you want to keep in mind. And the second part here is locality. So signals, natural signals, are local. So there is information defined in a neighborhood of your signal. And as you go away, the information starts changing, okay? So locality and stationarity here. Moreover, how do we make up this kitten here? With multiple kind of patterns, right? So we have patterns and patterns, and then we have patterns of patterns and patterns of pattern on patterns. So there is also a notion of compositionality, right? So we need to have different kind of, like we have several layers of abstraction we can see. So if you go down to the pixel space, you can see edges. But as you go a bit further away, you can see some kind of shapes. And if you go back again, you're going to see the whole cut. So there are three main concepts here we want to keep in mind. The first one was, help me, stationarity, which means we observe the same pattern over and over again. Then we have locality, because things are meaningful only in small regions. We don't care about things that are further away. And the third one is compositionality, which means things are made of larger things that are made of larger things. Very well. So let's keep this in mind. And let's see how we can exploit these three specific characteristics of natural signals in order to improve performance of our neural network. Okay, are you excited? Very well. All right, so recap from yesterday's lesson. Fully connected layer, just the classical neural net we have seen yesterday. They are also called multi-layer perceptron. They are also called dense layers. You can call them fully connected. You can call them as you want. I use this notation here. So we have an input at the bottom, because I said last time, you're going to be putting the input at the bottom all the time. Because this is makes sense, because here we have the low-level features. As we go higher in the hierarchy, we have higher level features. So we go high in the hierarchy as you proceed up in the network. If you have it upside down, doesn't make sense. You go up by going down. Doesn't work. So we are going to have the input at the bottom. Here we are going to be using a affine transformation with perhaps a matrix W, and then we apply a first nonlinearity F. After that, we are going to have the hidden representation. We perform another affine transformation, another nonlinearity, and then we get our prediction. Is why my y hat. The hat means, oh, this is not the actual target. This is my prediction of the target, whereas y is my target. All right, and these are the formulas, which are just representing this pretty chart over here. Okay, no new things. It's the same stuff we have seen yesterday. All right, so the function, the nonlinear function, can be the positive part, the sigmoid, for example, the logistic sigmoid, the hyperbolic tangent, and perhaps the Boltzmann function there. All right, so how does neural network work? Basically, if here I plot x is like my x here has 5 elements. So in this case, my input vector has 5 as a dimension. So it's one-dimensional tensor of size 5. Then I'm going to have my first hidden layer, so I write H1. Then I may have a second hidden layer, right? So we start making deep neural networks. Whoa, right? How can we make it deeper? Let's put a third hidden layer. Whoa. All right, let's finish, right? Let's put an output there. I have my y hat. So
what happened to the low hierarchy? Now it's left to right.
Yeah, because I had to, there is no space. So, or from left to right, or from bottom to top.
Okay.
Never from right to left or top to bottom. Okay, so, or this way, or you just send it down that way.
Do all hidden layers have to have the same
No, it's just
okay.
because I did copy and paste.
Oh.
Right, good question though. All right, let's go on. So the first X, the input layer, is also called activation at the layer 1. So this is my first layer of my neural network. So the first layer corresponds to the input, and also it can be called activation at layer 1. Then the same, the hidden layer, number 1, it corresponds to the activation at the second layer. Activation third layer, activation to the L, generic layer, and the last layer, of course, you can guess, is going to be the activation at the capital L layer, which is my total number of layers. All right, so we go from A1 to A2 by using the first weight matrix, right? W2 to go from the 2 and 3, W3, and WL. So let's pay attention to the first output. So this is my first element of this vector, okay? So how do we compute this guy here? This guy here, it's simply the row of the matrix times my vector, so it's a scalar product, plus the first bias is the first scalar. So that guy, again, is the jth row, if I consider the jth element, right? Is it okay? You're kind of perplexed. Yes. Oh, you're fine, okay, very nice. All right, so, and this one, you know, it's the user definition of scalar product. You just multiply and sum all the components. So from the input, we have these guys going here, whereas each of these lines is representing one of these weights over here, right? And then if we consider the second element, we are going to have all the guys there. And for the other guys, the same, right? So every time we have every neuron here, so these are also called neurons. Each of these are neurons or activations. So each of those are basically the scalar product between this one and each singular row in the matrix, right? And then we apply the nonlinearity, and so on for everyone. So this guy here sees all the input. This guy here sees all the input. And every neuron sees everything that happens in the previous layer. Same if we want to go to the second hidden layer, to the third activation, I'm going to have those connections, which are stored in the W2 matrix. And so on. For the third layer, all these connections from the W3. And finally, we have our output layer with all the connections with the WL. Okay? So this is, again, just recap. But I'm showing you a lot of connections, which took ages to draw. Okay? Right, pay attention. Since I'm lazy, I'd like to draw less lines. Let's see how we can improve this diagram. All right, next one, locality. Right, so what is locality? Can you remind me, please? Just speak. You don't have to raise hands. I don't know what raising hands means. Just
features of the neighborhood are same.
Right, so features, we just care about things that are close together. We don't care about looking further away because, you know, I care about what's here. What's there is like unrelated, basically.
But what happens at the boundaries? Let's say like cats, let's say height boundary or something like there. If you pick a pixel.
Right, so you can decide different sizes of how far away you look. So you can look like 3 pixels away. You can look like 5 pixels away. I'm going to actually talk about this in a second. All right, so let's go from the layer L-1 to the layer L. Here we have every one of these first input goes to the first neuron, so on for the second one and for the third. So overall, we have 5 times 3, we have 15 connections, right? All right, so from L to L+1, here we have just 3 connections. As we said before, we don't care too much for this neuron to look what happened very further away, right? Because we have said we don't care about things that are further away. So in this case, we are going to just have less connection. We drop these 2 connections here to this guy and this guy over here. The same for this guy and the same for that guy. So overall here we have 9 connections, right? Less drawing time for making all those lines. So from 15 to 9 by just dropping connections that are coming from input that are further away. That one doesn't change. So as we move from left to right, we increase our global view. So what does it mean? It means that this guy over here, so this guy here observes just 3 guys in the input. As you move to the right-hand side, this guy sees basically 5 inputs, right? If you move one more on the right, you're going to be seeing many inputs here. So as we go on the right-hand side, we increase our understanding of the overall big picture that we are looking at. So we define now something that is called receptive field. What is this receptive field? Which is something that your friend was mentioning before. So the blue guy here sees only 3 neurons from the previous layer. And so my receptive field here is going to be 3. It sees 3 items. On the other side, also this guy here sees only these 3 guys over here, right? So my receptive field for this guy is also 3. What is going to be now the receptive field of the output with respect to the input? Can you guess? Can you guess?
3 times 3.
She's 3 times 3, 5. 5. Oh, 5. This is 5. Sorry, I copy and paste. Exactly, right? This is 5. So this guy here sees 5 guys here. So the more you move to the right-hand side, and the more the receptive field increases with respect to the input. All right. Yeah? Or is there someone making noise? No. Okay. All right, so next one. So that was locality, right? We just care about things that are close together. What is this? Stationarity. So before we start, we start right now with this kind of less number of connections, right? We just start with the 15. 3 times 3, 9 connection rather than 15. So before we actually had those extra 2 connections, no, for the first guy. Over here, what do we do now? We are gonna be drawing these first guys here in yellow. So they look exactly like the white one. Okay, never mind. The second arrows are gonna be orange, perhaps, if you can see the color. And the third one here are gonna be red. So what does it mean? This guy here treats these 3 guys in the same way as this guy here treats these 3 guys, as the same way as this third guy here treats this input. So if this is a kernel, is a set of weights, I'm using the same set of weights for every neuron. I don't want to change. I don't want to have 9 different weights. I just have 3 weights, which I'm going to be reusing across my different neurons. Okay. So big difference. We have different weights for every edge. Here we are sharing. We are sharing the weights. That's why it's called parameter sharing. We share parameters across different neurons. And here I collect these 3 arrows as my kernels. In this case, it's just a vector of 3 elements shared across the different neurons. So this allows us to have faster convergence of our training algorithm because we have less parameters. We have less things to tune in order to reach convergence. Yeah?
Sorry, can you repeat what those stars are?
Yeah, so this one here. So every arrow here, every edge represents a weight.
Oh, okay,
So these 3 are 3 numbers representing my 3 weights.
Oh, okay.
And this one is called kernel. I should actually write it kernel. And this is reused by these 3 guys. So one kernel is associated to the layer and is reused at every position.
Okay.
And if you're familiar with convolutions, this is simply convolution. You have a kernel here, and this guy is sliding across. All right, so by having less number of parameters, we can have a faster convergence. We have less things to tune up. You have less computations. We have better generalization because when we learn about a specific pattern for this guy here actually knows already what this guy learned. So given that you are sharing parameters, once you learn these parameters somewhere else in the image or in your input data, you can reuse that kind of knowledge you extracted from data elsewhere. So you can have better generalization for unseen patterns. It's not constrained to the input size. What does it mean? So if here I add one more neuron, I have to add new layers, new edges, right? And here I have to retrain the network because I don't know if I have an extra neurons here, what are going to be the values for this extra neuron, right? Here, since I'm just reusing these values across the whole input, I simply can add a new input here, and I simply use the same values overall. Yeah?
A naive look though on this would be like that since you have less weights, this thing is gonna be not as performant as the fully connected. And I say naive because probably you have some answer to that. So
yes, so you're gonna see something very soon in the demonstration on the notebook. Okay, so you're gonna see something very soon. So if you have the same size, same number of parameters, this kind of sharing weight is gonna be super hyper performing. Like it's gonna perform much better, right? So if you have the same number of parameters, this one can have many more patterns you can learn. Because here basically those things that are further away, they don't really care. They never learn something very meaningful because things that are further away can change. They are not related to the close part. So if you look at something close, you have some uniform statistics that is happening again and again around. If you think about things that are further away, they can be anything, so they are unrelated. So this guy here basically they learn to be zero, sort of. They want to be invariant to whatever happens further away. So in the fully connected layer, when you use natural data, basically you're wasting connections because these don't bring any information inside the game. So even though you're going to use the same number of, let's say we use the same number, not the number of parameters, the same size. So exactly one-to-one correspondence. We drop number of parameters here. You don't see any lack of, in performance, any worse performance, because these extra connections don't bring in much of an improvement, okay? Because they are further away. So it depends, okay, with which kind of signals you are using and how many connections. Here I just show you 3. You can choose 5, you can choose 7, right? You don't have to limit yourself to 3.
But locality is the property that makes this.
Ha, that's correct. Yeah. So you're gonna see very soon what happens if you are evil and start messing with the data, okay? You're gonna see that very soon. So, faster convergence, better generalization, not constrained to a specific input size. Kernel independence. Ooh, we have done parallelization, right? We have done that thing yesterday. Some guy was talking about parallelization. Do like that with your head so I understand you have done that. Good. So given that these parameters are just working independently, you can parallelize drastically this stuff because you don't need to, they're independent. So they don't have, how do you say? Okay, they are independent. You know better what I'm trying to say. Last one, again, given that we are using sparsity, given that we are using sparsity over there, we have a reduced amount of computation with respect to the fully connected network. Yeah?
So I understand with stationarity, we expect certain patterns to repeat sometimes. So we don't expect it to be like periodic with period equal like 3 or 5 pixels, right? So it seems like a much stronger assumption than just like some patterns.
Okay, I understand what you're saying. So here, you're trying to look for this pattern here. And maybe you have it, so you get a high activation here. Here and here, you don't see the same pattern. So here you're gonna have a low activation and a low activation. But you're just looking for this 3 long pattern. So you just look for these 3 long pattern everywhere if you have a long signal. Let's say you have like a signal with 100 units, you just have this little kernel going down all the span of your signal. You just get out this higher activation whenever you find a signal. You just find it perhaps just in one location.
Yeah. So in that context, so when you're training and it sees the pattern somewhere, right? Because the weights are shared, so by backprop it learns to change the weights, and at some other part of the image, it doesn't see that pattern. So wouldn't it like screw the weights up?
That's why you have multiple kernels. So every layer, you have multiple kernels, and every kernel tries to specialize on a specific pattern with which it resonates. So when it gets some excitation, because, oh, I found my pattern, it gets very excited, and then this gets rewarded, and it starts growing. If it doesn't see the pattern, the backpropagation, so the gradients, when you perform backpropagation, we didn't talk about backpropagation, but anyhow, when you compute the gradients, you multiply by the input, right, the activation itself. If the activation is 0, low, there is no gradient. So the gradient gets killed, right?
So once it reaches a minimum, it stays.
So every time you get something excited, the gradient, bam, gets boosted. How do you say boosted? Yeah, boosted. And then you get that kernel to improve better, right? If that kernel doesn't see anything, it doesn't even get any kind of, it doesn't get to change its own values. But good point.
With random weights,
you have to shout because I'm deaf.
With random weights, is it supposed to know what it's looking for, that kernel?
Okay, I have a lesson on that too, but you should come to my class or just look my videos recordings. Anyhow, when you start with random weights, you have a chance of observing a specific kernel, a specific pattern. Anytime you observe that pattern, one of your weights, one of your kernel is going to be a bit stronger than the others. So the one that is a bit higher gets improved, and when you go up with one, the other one are getting pushed down. So basically, when you find one of your randomly initialized kernels to start resonating with a specific pattern, it's going to be strengthening its own response to that specific pattern, while trying to push everyone else down for that specific pattern. Does it make sense? No? Yes? No? You can say no. I try again.
No, but I can.
Oh, okay. Other questions? No? Should I keep going? You like it? Yeah, question.
So the kernels are competing with each other to isolate one
Yes,
feature?
yes, but I didn't say that. That's what happens if you check how the training mechanism work, which I didn't actually explain. But yes, every kernel is going to be specializing in a specific feature, and whenever it is specialized, it gets to improve its own performance
And
with that.
that kernel's focus.
Yes, it's going to be every kernel is going to be focusing on a specific kind of pattern.
Okay.
Okay.
Yes.
All right. Other questions? No? All right. Shall we go on? No. People are sleeping. Hello. Hello. You're back. All right. Let's go on. More pictures. Okay. So how do we use? Oops, sorry. What's happened? Okay. How do we use this convolutional neural network with, let's say, images? Because that's what I play with for most of my PhD. So this is a standard neural network. I'm going to try to explain now some of those components. So for the first part, we're going to have multiple layers. So here I have like multiple D blocks, which are my discriminators. For example, I have multiple blocks which are containing some convolutional module layer. So we have multiple layers, deep networks, which are convolutional because we'd like to share parameters and make them sparse so we don't have so many computations. And so these two things are basically summarizing the three specific characteristics of natural data, right? We said it is sparse, it is locality, stationarity, which is used by this guy here, and then is compositionality, which is used by multiple layers, right? And the receptive field concept. So these here are how we exploit those three particular statistics. Then we have nonlinearity. Why do we have nonlinearity? If you have just linear layers, what is the output of a matrix multiplied by a matrix multiplied by a matrix multiplied by a matrix? Just a matrix, right? It's all collapses down. So you need nonlinearities in order to keep those things from collapsing. Then we have pooling. What is this stuff? You're gonna see soon what it is. Batch normalization. This is actually what you're gonna be using every time you're gonna be training networks, which is improving speed for the convergence, and it also adds some kind of very good noise, which allows your network to generalize better. I know I said many things. If you didn't understand, it's fine. Just use this stuff. Works very well. Last one, residual connection. One more thing is been very popular recently is to skip connections. So here you go from the bottom layer to the second layer to the third layer. But then every time you initialize this stuff at the beginning before training, this stuff is randomly initialized. So things that come here get distorted, more distorted, more distorted. Here you have just crap. So given that you perform this extra connection and some here, whatever is here, the network can decide just to turn off this guy. And therefore you start with a smaller network. And then maybe if the network needs some more modeling power, then it actually starts using some of this modeling power here. So, but these residual connections are something that are really, really good because that help your network start with little tasks and then it starts growing basically in modeling capacity. So these two guys is something you're going to be always using in your network. Yes?
I have a question. I might have missed it, but what does D1, what are those rectangles?
These are coming from a copy and paste, I guess. So those are discriminator blocks, discriminative blocks. Okay. That's why I call them D. Because I had also a thing coming down which had some kind of generator. or
Okay,
yeah,
so
something.
D discriminator block 1 through L.
Yeah, okay, you can just think about those as layers of your neural
Okay,
network. Okay,
alright.
nothing fancy. But each of those contain a convolution, a nonlinearity, maybe a pooling, which I haven't explained yet. All right, so let's see what poolings are. Oh, okay, sorry. Actually, let's see how it works. So in here, I provide my image at the bottom. And it's like a 3-layer, maybe image, because it's like RGB layers and has a spatial dimensionality too. And at the end, I have something that is like more of a vector, which each element may be telling me the likelihood of observing a specific category if we are doing classification, as we have seen yesterday. So in case of yesterday, we had like a vector of size 3, whereas each point was expressing how likely is to have that point belonging to one of the 3 spirals we have defined. So we start with something that is flat and large, right? So it's like very thin and very large, and we go with something that is 1 by 1, so it's very narrow underneath, but it's very long, right? So in between, what do we have? In between, we have something in between, like in the not that spatial. There is not that much spatial information, but we have much more thickness in this sense here. So the information that is here, if you think like not like mathematical information, just information in the English way, or like just easy way. The term that you use in English, not any kind of specific information. So the information contained in this part here is the same information that is here. But here, the information is expressed as a spatial information. And here, as you go up, the information is actually encoded in the depth of this kind of representation. So here, the spatial information may represent where the position of the ear of the cat is, where the nose is, where the eye is. And the depth in the image, it tells you the color, right? It tells you something that is locally defined in that specific point. Yeah?
Would you have 1 per pixel?
Here?
No, up.
There?
Yeah.
So this is like 1 by 1 pixel.
Yeah, so you'd have, for your entire image, would be like 1 of those per
You have,
pixel. Yeah.
this is just 1 for the whole image, and each element here may tell you what is the likelihood of observing like a cat, a dog, a horse, or anything. So here you have descriptive information, which is not any more spatial, but it's like telling you the likelihood, the probability of having a specific item if we are doing, for example, classification. Whereas here the information is spread in the spatial dimension. So from spatial to descriptive. And in between you get a halfway representation. And here we go from thin to thick. All right, I'm almost done. So pooling, I said, right? What is pooling? So let's start here by drawing something. I've just drawn the top corner of my kitten picture. So here I can represent my 4 pixels in the top left corner. I can get those pixels and compute the p norm. What is the p norm? It's just that thing there. It's the p root of the summation of each element raised to the power of p. So if you have basically the Euclidean norm, you just have the number 2 there, right? So you have the square root of the summation of the squares of the items. If you have the 1 norm, you just have the summation of the absolute values, right? If you have the p going to infinity, then you basically have the max, right? So if you have the max norm, p goes to infinity, you have the max. So basically, given those 4 pixels, we can extract the maximum value, or we can extract like the norm value, or you can extract whatever thing you want with the p pooling. Okay. So most of the time, you're going to be using max pooling, which is basically this guy here. So we have the first guy there. We perform the LP norm, and we get our output over here. Then we are going to be moving our basically window across the next 4 pixels. And again, we are going to be performing the LP norm, and then we have our next value. Okay? And we do this stuff across the whole image. So if we perform this operation on the input image, what is going to be the output of this operation?
Smaller image.
Smaller image, right? Spatially smaller. Sweet. So for example, if I started with an image which is m by n, I end up with m half and n half if I use these kind of parameters. My channels here, C, are going to be the same channels here. We didn't change the depth of the information. We just changed this direction. So something you want to keep in mind, what's happened. This was my activation at specific layer. I apply pooling, and I have how much information did I lose here? In a fraction?
75%.
In fraction, what's Oh, okay. So how much information did I retain?
25%.
1/4.
1/4. Okay, thank you. I don't know percent. All right, it's confusing. All right. Anyhow, we have retained here 1/4 of the information. This is considered a very, very strong bottleneck, which means you're going to be losing information. Really, like it's bad. So what is a very good practice is going to be having the convolutional layer actually expanding this guy. So if you start with C channels, you're going to be ending up with 2 C's channels, so that when you cut half the X and Y dimension, you just go to 1/2 of restriction of information. Does it make sense what I say? No, hold on. Just let me check first if people understand. So first we said by applying pooling, we shrink, if it's an image, by half and half, so we get 1/4. So if I increase twice the channel size, I'm just losing half, right? Okay, yes, no?
So channel size, you mean the number of values that I can take, for example, that index I.
So the channel here?
No, that index I up there, that's the RGB, right? The value of, the amount of R, the amount of G, and the amount of B.
No, these one here are simply 1, 2, 3, 4 guys here.
Okay.
So this is applied to every channel. So for every channel, I perform this kind of shrink down.
So this is like, it's also, I think it's called smoothing, right? But did you tell us why are we doing this, or you're just explaining the procedure?
I haven't told you why.
Okay.
You can ask why.
Yeah. Why are we doing this?
All right, very good. So why are we doing that? I slept not too much, so maybe I forgot. All right, so why are we doing that? Because there are too much data in the beginning. We have so much spatial data, and we were trying to go from those large representation to something that is narrow, right? You just remember the slide of before.
Yes.
So we were like large, and then we go narrow. So we increase this dimension by using convolutional kernels. By every kernel gives you 1 point there in that vector. And then by using this one, we can reduce the spatial information. So we go from our spatial image on the bottom to something that doesn't have any more spatial information, but is just a descriptor of the image.
So just one question. So if I took so in principle, image can have different detalization. Does it mean we're just looking on the same image from different detalizations?
Yes, that's correct.
So for example, when you have some print in a newspaper, if you look like this, you will not see anything. But if you move far, you will see picture.
Yeah.
So that's what we are doing.
That's,
We just
yes.
trying to produce different layers on different detalization to see different size of objects.
That's correct. So we perform this for different reasons. One of these reasons is to have different kind of zoom-in factor of our data. So the more you apply these operations, and the more you have a global view, and the more further away you go from your newspaper. The other reason is that we are going to be lowering the amount of data we are dealing with.
There's something that confuses. So in that picture, we had a flat image, and then at the end we have classification, right? Yeah, we start from the image, we end up with classification.
Yeah.
This is done through neural net, those layer, whatever conversions we do. But now, next slide, you're showing us how to do it by hand. Force that narrowing.
So you change this dimension here.
Yeah.
From large to smaller by using this pooling operation. You increase the thickness by using the convolution.
So this whole thing you're describing, pooling, I thought this was just an end product of your whole neural net.
Yes, this is my neural network.
This is your
And each of these blocks contain a convolutional layer, a nonlinearity, and the pooling operation. It's like a sandwich.
So it becomes flat that there's also fully connected layer in the end, and you flatten the output and apply a fully connected layer. But it's square as it goes through convolutional pooling.
So what is your question? Sorry, didn't understand.
So my two things, I guess, if you remove this pooling,
Then everything is going to be the same size.
I mean, when you go through layers of a neural network,
Yeah.
do the conversions, the pooling is something additional you're trying to add now, or it's always there?
So if you don't apply any pooling here, from here to here, you're going to have the same spatial location, but you just increase this thickness. So every time I do a convolution between this one and my kernel, I get the first plane. Then I do this convolution between this one and another kernel, I get the second plane here, and so on. So here I have multiple outputs of multiple kernels. But the spatial information is the same. It doesn't change.
But if you have less number of hidden units, then doesn't it?
The hidden units are representing the thickness. So if I have one linear unit, I'm gonna have just one like this here. So the number of linear units before I was showing you fully connected layers. In this case here, let me go back.
It's not the number of...
So this guy here, if you can think here, despite the fact that here there are 3 and here there are 5, you can think about here having also 5, and the other guy gets input from outside. So whenever you apply convolution, you're going to have the same number of input and output. So if we go back here, if I apply a convolutional kernel to this guy, one convolutional kernel, I get exactly the same guy here, the same spatial information. I mean, with the same dimension in the space. If I apply the second convolution, then I have the second layer. So if I apply 10 one, I'm going to have something that is 10 lines long. But then again, I would like to remove this spatial information so that I have like one vector. Yeah?
So these different kernels and things below, that's what C on the next page?
Say again, sorry?
So on the next slide, you
Yeah.
have C, which is like, you do this more than once. So it's the depth.
Yes, yes.
And
So
that depth is the different kernels.
the C is the height here. I should put that notation here. There was another question there. Yeah?
So but earlier you were talking about like RGB values.
Yeah, so here I have 3 layers, 1, 2, 3 in this guy here. But here we have maybe many more.
Okay.
So if I have 3 here, the thickness of this guy here, this might be like 20. I don't know.
Okay.
And this may be the size of my, number of objects I'm trying to look for.
So C starts as 3 and then
Yes, that's correct. If I use color images, yeah.
I guess what confused me is that even if you're at the end, you always have 1 by 1.
If I would like to perform a classification task, yes.
Regardless whether you do pooling or not.
If you don't do pooling, you will never end up with 1 by 1.
The end decision is always...
Yes, but I have to change the size of this stuff, right? So if I apply pooling, this becomes half by half. If I apply pooling, it's going to be half by half, and then I'm going to end up with 1 by 1 at the end.
So final decision is this kind of pooling.
The final decision is going to be applied on the whole image. Okay. All right, so I think that was it. So this was the final. Yes, I was also in time. So, and that was the final thing, right? How you perform the pooling operation. So at the beginning, first layer, we start with 3 channels. Then maybe you apply a convolution, you end up with 10 channels. Or let's say we go from 3 to 12. But then again, I'm going to cut half and half. So with one way, I try to increase the thickness of these guys. And the other way, I try to remove the spatial information. So here we have seen how a convolutional neural network is built and how we are going to be applying different kind of layers. And before we have seen a comparison with the fully connected layer, which has many more parameters. So right now we are going to be showing you a quick example about training two networks with the same number of parameters. One is a fully connected network, the other one is a convolutional neural network. So given that they have the same number of parameters, but the convolutional neural network is sharing those parameters, you may have many more kernels with respect. I mean, you have much more modeling capabilities. So we are going to see how they compare by using natural images, like, let's say, pictures of numbers drawn by some individual. And we are going to see how they perform, the convolutional network and the fully connected layer. Then we're going to see what happens, like your colleague was mentioning before, if one of these hypotheses are not there anymore. So what does it happen if locality, stationarity, or compositionality are going to be going away? And we are going to be seeing very soon what is the result. Other questions? Yes, please.
I'm just curious, for the residual bypass connection?
Yes.
Do you use that for the same reason you would like implement dropout, or are they?
No, this one, right?
Yeah.
So this one I use for, okay, let's think we are gonna have 100 layers and there are no bypass connections, okay? When we initialize those networks, we initialize them usually with some small values towards the zero. When you perform the computation for getting the partial derivative of the loss function with respect to the parameters, you perform like basically the multiplication on the final loss derivative with these weights. No, so if you perform some when you perform the chain rule with matrices, you basically multiply the gradient by the input. So given that those values are very, very tiny, you have a tiny signal at the end multiplied by something of which eigenvalues are all small, right, towards zero. So you have some signal here that is basically dying through the network. So all these guys down there, they will never be trained. You know what? Where is your input coming from? The bottom. And where do you send your input through? Trash, because it's noisily initialized, right? So you have your very nice input, and you just destroy all the statistics, sending it through a random crap. And something starts changing here in the upper part, but those things really never change. When you apply this kind of bypass connection, residual connection, or residual bypass, or shortcut connection, three names for the same shit. Sorry. So in this case, you have the gradient coming down, and then it goes down here. So this guy is going to be using the same gradient that this guy is observing in order to optimize its own parameters. So these guys are absolutely essential if you start doing networks that are kind of deep. Otherwise, you have some problem that is called vanishing gradient. Those gradients, basically, given that are multiplied by matrices with small eigenvalues, they vanish down. Or even worse, if those weights are getting, you try, okay, I don't want to lose my gradient. I increase those weights. Those weights are very nice. They are large, and you have like eigenvalues that are larger than 1. And then, boom, you have exploding gradients. So it's very kind of finicky thing. So if you just add those connections, everything will just work fine. Also, that's why we use this one, sort of speaking. This is so good. If you are familiar with like fiber optics, sometimes you have those repeaters in the fiber optics. Are you familiar with fiber optics? No. Are you familiar with transistors? Yeah, all right. So why are you using a high impedance transistor after another transistor? You don't want the transistor that is on the afterwards to load your first one. Otherwise, you just drag everything down, right? So these guys here are basically some kind of impedance matching. And they are separating every block. So this block doesn't load my previous block. And so I put everywhere those batch normalization, which allow my network to be like independently training each separate block without having this kind of loading side effect, okay? So these two things are really, really essential. I could have a lesson just on those two, but I just put them there because you had to use them. I mean, I highly recommend. Last summer school I taught 2 weeks ago, there was just one guy who applied this guy here, and he won the challenge of the summer school. He won like the prize, so I was like, yay.
How much was price?
I don't know. I think it was a book from machine learning stuff. It was very nice.
How much was that book? I just interested in a number.
$40. $40. All right. So that was it for the introduction to convolutional neural networks. Right now we're going to see this exercise, if everyone is okay and you don't have further questions, where we're going to be playing a little bit with the notebooks and see how they perform. Okay? So let me introduce here my colleague. Please come in.
All right, so Alfredo gave a nice overview of the fully connected and convolutional neural nets. And at some point of the exercise, we had, basically we compared convolutional fully connected neural networks and how every neuron from the previous layer has to be connected to every neuron in the layer after that. Thank you. In convolutional neural networks, we basically take advantage of the locality, which is one of the three basically properties of images is locality, stationarity, and the compositionality, to reduce the number of edges and connections, and basically we have the receptive field. So I'm just repeating a little bit what he said. And right now, let's basically look at the specific example and kind of get hands-on. So you can follow that on your laptops, or for those who have succeeded with the setup of the Jupyter Lab, you can just go in the Jupyter Lab. So I'm gonna go and start the terminal window. Here I have my exercise in the workspace, and I did have to do git pull to pull the latest changes from yesterday, as we added one more notebook. Maybe reset this printer. Reset, maybe, because they may have changed something. Sure. And the notebook we're going to need is the notebook number 5. Yeah, so if you did make some changes in the notebooks, which basically most likely did, because as you run the notebook, it saves the outputs, and when you try to do git pull, it won't let you. So you can do git reset hard, and then git pull. Or you can just follow it as a demo. So let me ask first, how many of you have used any deep learning frameworks in the past, not counting this school? Who have used deep learning frameworks, any, like Keras, TensorFlow, PyTorch? So about half. How many of you used PyTorch? Just a few. How many of you used Keras? So yeah, most of the people who used deep learning frameworks used Keras. All right, thanks. Yeah, so yeah, for this exercise, we're going to use PyTorch, but I'm going to try to make connections to Keras. So the first cell, there's nothing special. We just import torch. Then we import the NN module, which is what we're going to need to basically construct our neural network. The optim module is for optimizers. This is where all the optimizers live, like Atom, RMS prop, SGD. So we're gonna need the data sets, Torch Vision data sets, to import the MNIST, which is what's gonna be used for this exercise. And of course, Matplotlib for plotting, and NumPy also. As we're gonna be plotting it, we're gonna be converting it back to NumPy. And functional, it's going to be used for activation functions. You will see. All right. So the first step is simple. Let's just load the data set. And this is just a copy from what's recommended in the PyTorch MNIST tutorial. You can see familiar steps here where we load the data, we physically download it to the folder, then we normalize it, we shuffle it, and also we batch it. We assemble it into batch-sized tensors. I personally, so for this we do the shuffle for the testing step, but that's strictly speaking not mandatory. And let's take a look at a few images here. Those are familiar to you, the handwritten digits from MNIST dataset, so nothing special here. Those are 28 by 28 images, 28 by 28 pixel images. All right, so so the purpose of this exercise is we're gonna construct the fully connected and convolutional neural networks. We want to make sure that they have roughly or like almost exactly the same number of parameters, and we will see how well they do on this MNIST data set, and then we will try to break up some of the assumptions that Alfredo was talking about, in particular the locality by scrambling the pixels, by shuffling the pixels in some random order, and see how well they do after that. So for those, so basically there's two, strictly speaking, APIs to construct a neural network in PyTorch. One of them is very similar to what we used in Keras. So in Keras we have two APIs, sequential and functional, but both of them we kind of put the layers one by one as the Lego blocks. Something that I have here. This is basically, I'm defining the whole logic of the neural network as one sequence. And this is for fully connected network, which will consist of two linear layers followed by a ReLU nonlinearity with the one more layer followed by the softmax output activation, which is what we're going to need for handwritten digit classification. So it will output the vector of floating point numbers, which we will take the maximum probability and assign the label according to that. So in PyTorch, it's a little bit lower level than Keras. We typically extend, we prepare a class derived from an N module, which is going to be the base class for all the neural networks you write in PyTorch. Here you would override the constructor, and you would basically invoke the base class constructor via the super method, adding additional methods which are not present in the base class. In this case, it's the input size and the logic of the network. Finally, we need to override the forward method, which is the logic of our forward pass. As we train, we have the forward pass, which in this case is going to be a bunch of affine transformations followed by nonlinearities. And there is also a backward pass, which is the partial derivatives chain rule differentiation, which comes for free to us in PyTorch, but we still have to call backward on the loss, as you will see later in the training loop. So here, yeah, basically the forward pass is super simple. we just take those square images 28 by 28. To be able to feed them to the fully connected network, we have to flatten it. And the view in PyTorch, as Alfredo introduced yesterday, is essentially like a reshape in NumPy, but it doesn't make a copy, so that's why it's called view. And we flatten it to the input size. We have to be sure that the input size is actually what we pass in the as we're gonna use this has to be 28 by 28. All right, and next is the ConvNet. So here, on purpose, I use slightly different approach. I didn't put it all in one sequential model, but I broke it down, creating basically a member for each layer. And we'll have here two convolutional layers, conv2d layers, followed by two linear layers. This is actually exactly what Alfredo had in this picture on the right, from top to bottom, from bottom to top, except he was calling the D, which I'm guessing from some generative adversarial discriminated generator. Yeah, so, and don't pay attention to this like multiply 4. It's basically the goal here was to tune the number of parameters to match between the fully connected layer and fully connected neural network and the convolutional to prove our point. Okay, in this, if you define it like that, as opposed to sequential, would have more interesting looking forward method, which you mandatorily have to override in each neural network which you write. So it just basically goes from the outermost to the innermost layer. First you go to the convolution, when D, ReLU, pull in, convolution, pull in, flatten, fully connected ReLU, fully connected softmax. All right, so then we just need to shift enter. So this thing is, the thing is in PyTorch, similarly to Keras, we actually write in pretty much device agnostic code. And basically, if you have a GPU, it will pick it up. It might be a difference in dependencies. Keras depends on TensorFlow, so to run on TensorFlow, you have to pip install TensorFlow-GPU and make sure that the CUDA drivers are in place. But if you don't have a GPU, you just run on the CPU and you don't have to make any changes to your code. Similarly, if you define a device string like that, it will switch to the CUDA if you have GPU. If not, if it's not available, it will just run on CPU and you don't have to make any changes. So this is the, again, for the, yes?
Quick question. So I'm still stuck on the convolution thing. If you just go back a little bit, it says kernel size equal to 5. Does that mean 5 units in the back is connected to 1 in that? That's the meaning? Yeah. Okay. So there are two layers you put there, conv1 and conv2. The first one, it has in channels equal to 1, and the next one, it says in channel is set to be same as n features, and I'm not sure what that means. Why? Do you see the first one, the arguments is 1 and n feature. The next one is n feature and n feature. I'm trying to understand why the difference is.
So here, basically, we're free to kind of adjust the parameters as long as they're consistent across layers. And here the main goal was to get a neural network which would have the same number of parameters, trainable parameters, as the fully connected layer. Right, so you know you can control the number. So the parameters you can fix as you define your convolutional neural net is the kernel size. You can also fix the padding. You can fix the stride as you move the kernel width. It can be 1 or 2 or more. So there's nothing wrong to have the same number of input channels. Maybe I'm missing the point, Alfredo. Do you know?
So you're going to use this conv1 and conv2 differently inside your neural network.
Yes.
The first one is conv1, then later on you use conv2 after my.
Does it work? No. It's okay. Just be loud. No, because it's not gonna be. It's not gonna be recorded otherwise. Okay. So here,
Unless you're very loud.
we go from basically one channel because we are having a black and white image. So we just go from one layer to any kind of number. So let's say 5 layers. So we have 5 different kernels. Those parentheses with the 3 stars I put there. We have 5 of them. There are no 3 stars. There are 5 stars because we are going to be considering a neighborhood of 5 pixels. In this case, 5 pixels times 5 pixels. So these kernels are 25 values, and I have as many as this guy. How many is that? I don't know. Maybe if this is 3, I'm gonna have 3 kernels of 25 elements. Okay. So the second one we are gonna be having. We start from one layer thickness input image, and we end up now with we said 3 layers, right? So afterwards we are gonna be using convolutional kernels, which are gonna be going from 3 thickness to again 3. So this means that my kernel, in this case here, was 5 by 5. In this kernel, this case here is 5 by 5 by and 3. And how many I have? This many. So this is 3. Okay, if this is a different number, let's say this is 4. So you have 5 by 5 times 3, because this was the size of this guy. And then I have as many as this guy. So I have 4, 5 by 5 by 3. Okay? Does it make sense? No? You can say no, I can try again.
I see what you're saying. So the 3 different colors have been processed separate.
Oh, here we just have one color.
There's only one color.
Okay.
It's a grayscale image, so there's one input channel.
But if there would be 3, I would just process them all together. So if this would have been 3, this would have been 5 by 5 by 3. And then I have this 3-dimensional tensor moving around and performing convolution around the image. Okay?
Yes.
Other questions? See this light projector, I can't even see anything.
Yeah, so the channels control the depth of the tensor, and the kernel will be in the XY plane.
It doesn't have to be divisible. It's really sliding. It's not divisible.
All right, so let's move on and look at the training loop. So in Keras is a high-level deep learning framework, and we usually work with something called estimator. Estimator, it's basically something you define, and then you just call .fit on it if you want to train it, or if you have, for instance, if you want to pass it on if you want to train it, if your data is a generator, Python generator, you can call .fit _ generator. And then once you train it, saved weights, you want to run a prediction step. So actually, if you have a validation step, at the end of each epoch, you would call .evaluate. And for prediction, if you want to get the actual predicted labels rather than just the metrics like accuracy and loss, you would call .predict. So this is all nice and simple until you want to do something custom. When you want to do something custom, it's very nice to have access to actual training for loop. And that's why actually in PyTorch we don't have estimators, or at least not yet, and we have to write our own training and testing loops. So here is the training loop. For convenience, we put it in the function. So here, this term, basically, it's the permutation, which is something that we're going to be using for the exercise to scramble the pixels. By default, it's a range, so it does no permutation. So here, as you can see, so steps as follows. We zero the grad. So basically, as we run the training steps, we're going to accumulate the gradients for each weight, and we have to zero those gradients before the next optimizer step. Otherwise, it will calculate incorrect values. So then we get the output of the model, which is the essentially what the forward pass gives us. And here we can define the loss outside of the training loop, but this is just fine. For this exercise, we use the negative log likelihood loss and give it the target and the output values of the forward pass. And so we have that, and we call the backward pass on the loss, and complete our optimizer step, which is just a weight update. Once we have completed the backward pass, we got the gradients, and in the optimizer dot step, we essentially apply the gradients to the weights to get the new weights. All right. Questions?
So you apply the gradient, a negative of the gradient with some sort of an epsilon factor on the current weights to get the new weight. So it's
Yeah, in the simplest case, in the simplest case of the stochastic gradient descent, we would just have the weights at the iteration I+1 equal to the weights at I minus lambda the weight update.
Right.
Right. So if you use some momentum, SGD with momentum, there would be something else. Or optimizers like Adam, they adjust the learning rate depending on the parameter to improve the convergence. But in the simplest case, that basically weight update is what happens here at the optimizer dot step. There was a question over there.
What does the perm do?
Sorry, once again.
The perm?
Nothing.
Permutation, but in this case, it's nothing. Because by default, it's identical range, so which means we keep the pixels in the same order as they come. This is actually for our second exercise where we have random permutation. I will show the pictures, so there is not going to be any magic involved, and I will show the pictures. Okay, so the test. The test is essentially the same. One thing that will differ in the training and test steps is that we won't have backward pass, right? So in fact, you can do model.eval. Here, this would set no gradient required. Alfredo skipped the auto differentiation lecture yesterday, but basically, yeah, we can switch off the gradient from the variables. And yeah, so here again, we do the for loop over testing data. We do the forward pass, we calculate the loss, and we accumulate it. In this particular case, we have the softmax output activation. So in NumPy, that would look like you would do np.argmax over the output of the softmax, right? So you want to pick up the index of the vector, which corresponds to maximum probability. And then we count the correct predictions. We have the correct values, which is basically the handwritten digits. Handwritten digit 1, 2, 3, 4, 5, 6. And pred.eq, we can substitute it with just an equality sign. I will show how to do that later. So this stuff is just to get it back from the tensor to the actual scalar, floating point scalar. So that will look a little bit ugly, and but we have to get used to that now. All right, I'm gonna hit Shift Enter. And so finally, before we go and train the small, fully connected network, we have to also, so here we just we defined FC2 layer. We call its constructor with the input size, number of hidden layers, and output size, hidden units, sorry. The number of hidden layers is fixed, of course. And we define the optimizer as the simplest, stochastic gradient descent, SGD. We pass the model parameters to it and define the learning rate and the momentum.
And that's all. We make sure that we take a note of the number of parameters to compare it to what we are going to use in the convolutional. And then we just train. Oops, and I'm running out of time. I don't know how it happened.
We only have after the break.
Oh, okay, so this is a time before the break. I was like, that was too fast. All right, so it's running. We see here the values logged at the output is the number of samples processed so far, and we also take note of the training loss. As long as the training loss reduces, we know we're doing okay. And I was expecting it to be faster, but hey. So,
a nice check to do is actually to check this first number. You always have to check what this number is. Can you do the E, the Neper number to this one?
Yeah.
Can someone use a calculator to compute this? E to this guy. You tell me. Okay, 11, right? So basically, what you expect this first number to be is going to be the natural logarithm of the number of classes you're training on. Okay, so if this number is anything away from the natural logarithm of 10, then you must be kind of worried something is kind of screwed up. Okay, and this is due to the fact that we are using the logarithm. Did you remember, right, from yesterday? We were checking the log of the correct class. And given that at the beginning all the classes have equal probability, given that the network is not yet trained, you expect to have 1/10. And therefore, natural log of 1/10 is the same of minus log of 10. So minus log of 1/10 is the same as log of 10. And so this first number should be matching that one. If it doesn't, you should be kind of worried, okay?
And so the training for a fully connected network finished. We got 96% training accuracy and 86% tests accuracy. Before we go, let's just start the training for ConvNet and go to the coffee break. So here, basically, we just have to do the same steps. We have to construct the model using the class we already defined above, and we're going to use the same optimizer with the same learning rate and the momentum. The number of features here is adjusted again to guarantee that we have similar number of trainable parameters. See, number of parameters is 6422 here, and in the previous case it was 6442, which is almost exactly the same.
And one more thing, so here we have mentioned there is number 6 of features. So we are going to have, just to keep in mind the numbers, we're having 6 kernels, which are 1 times 5 times 5. So we have a collection of 6, 1 times 5 times 5 for the first convolutional layer. So this is conv1. Then we have conv2, which was, how much is going to be? Still 6, right? So it's going to be 6 kernels. And this one was going from 1 to 6, right? So this one is going to be 6 times 5 times 5. So 6 because it has to match this dimensionality here. And 1 because it has to match the input dimensionality. Okay? Yeah.
So do these 6, let's say for conv1, do these 6 kernels move together, like scan together in the on the picture?
So they are gonna be. You have the initial picture here, and you have this guy here, and this guy moves across this direction and this direction, and it gives you the first feature map here. Then you have the second kernel. So you're gonna have the second guy. Then you have the, how many? 6. So you have up to the 6th guy here. So you go from 1, that is the input, my x, to my first h1 here. And then you're gonna be using these kernels here in order to convolve this guy for the second one.
But one more question. But is there any constraint that prevents these 6 layers, output layers of those 6 kernels to be different from each other? In other words, does it prevent those 6 kernels to not look for the same feature? Is there any constraint?
The constraint is automatically induced by the loss function. Whenever you have a kernel which is finding a specific feature, the other one will try to find other features. Because I said before, so as soon as you have one feature, one kernel resonating with one specific kind of feature, that is going to be strengthening its own response to that particular feature.
But that can happen to the second kernel as well, like responding to the same feature.
Right, so if 2 kernels are initialized the same way, they may learn the same stuff. At the beginning, we have random initialization. So basically, you're going to have, it's very likely that each feature, each kernel is going to be resonating with different kind of features, and then therefore is going to be optimizing for a specific target. So if there are no other questions, I think we can take a small break, get a coffee, try to run some more of the exercises like if on your machine if you didn't manage to follow up. And we come back here at, I don't know. Right, so 3:30, okay?
So just before we go to the break, so convolutional neural network finished training. As you can see, we got 96% accuracy on the training set and 94% on the test set, which is out of sample. And as a result, we can say that the convolutional neural network performed significantly better on this type of task. And let's see how well does it do if we're trying to basically remove the locality from our assumptions. And let's continue after the break. Yep. No. Actually, no need. I will say something else right after that. Actually, I figured why I didn't run faster because I.